new instruments. We all know that the radiation balance in the Arctic is very, very important. It's actually the key to this long diurnal cycle, especially the long wave in the polar night. And we're missing currently half or more than half, 60% of the spectrum or more is in the far infrared, and we have not used it so far, yet it's very, very important for clouds, microphysics, and it's sensitive to composition of the atmosphere. So we did focus on that, and I really acknowledge YOPP for the support and the momentum it has given us to get funding from various agencies, including CSA, Canadian Space Agency, NSERC, Calcul Québec, Compute Canada, Fonds de recherche nature et technologie du Québec, Pearl, and I'm part of the CANDAC group, and it's been a real good team effort in that direction. You see here the site at Pearl, the ground site, where we have our new instrument, the FIR Infrared Radiometer, side by side with the E-AERI, which is a similar instrument, high spectral resolution, and used as a validation. We have LiDAR, radar, and star photometer. And this has also stemmed formation of a consortium of 13 universities in Canada that are now working along that line for new satellite. So this is to summarize our status in that direction. So let's see. So we all know that the Arctic is not only a local pool of influence, but it's global. It does influence the transport of heat into the mid-latitude and the radiation balance in the high Arctic, control the ice and the snow. A lot of strong feedback. We all know about that. What's impressive is the size of the Arctic. It's 154 million kilometers square. And the side of it where transport is occurring is rather small. It's closer to the boundary layer. So we lose heat during the polar night only by infrared, which leads to ice extent, anomalies, and everything we know about. But this has to be compensated by some transport in the mid-latitude. And that here we see the polar vortex in action, carrying heat south and north. And this is the source of storm, all kind of storm, like even tornado in summertime. Cold Canadian air, as they say, our colleague in the US, is producing deep convection. It's producing storm in the winter. It's producing atmospheric rivers, all kind of anomaly. It's due to the cold air contrast with the warming of the planet at other latitude. One of the strong hypotheses we had to look at was the fact that the Arctic aerosol were polluted, so-called the Arctic haze. So we knew from the 80s about that. And this acid coating is an important effect on cloud microphysics. It's transported to the Arctic. It's lifted into the polar vortex and cold lows, and it produces thin clouds. And these thin clouds, when they're polluted, they tend to form larger crystals and fewer of them, and then enhancing precipitation. And these thin clouds are often reported by the ground as clear sky, although it's overcast for thousands of kilometers. And they're semi-transparent, and they're producing diamond dusting, and they're radiating from the volume of the atmosphere instead of the surface. So they're very efficient at removing heat into the body of the troposphere. And as it sediment, due to precipitation, it reduced the water vapor, and that changed the greenhouse effect, because water vapor is the strongest greenhouse gas in the atmosphere. So it can produce two types of cloud, thin ice cloud, type 1 or 2 we call, and the larger, the type 2 is fewer and larger crystals. Just to give you an impression of the size of it, it's thousands of kilometers. Just one example among many others, where you can see CloudSat and Calypso, and the overlap. It means that the crystals are big because the radar is sensitive to d to the 6th, diameter to the 6th. And here you have a 4,000 kilometer range of thin ice clouds that are semi-transparent, probably reported as clear sky. And it's diamond dusting in there. It's influenced by aerosol, and we see it clearly in this picture here, where a volcanic plume that are acid aerosol are producing larger crystals. It turned out to be during ISDAC campaign in 2008. And we can see clearly the precipitation coming out of the aerosol, acid aerosol plume. Now this, again, it's an Arctic cross-section of CloudSat Calypso, the A train, where you see the radar and the LiDAR and the radiation calculated from this probe. And note the radiation coming from the body of the atmosphere and not from the surface. These are our mixed phase clouds here in the boundary layer, and the radiation is coming right from the top of the cloud. It's warming from below because the ocean is open there, but everywhere else it's cooling. There's no warming source at the surface, and you can see in the background the water vapor also acting there. So we designed an instrument to try to capture the effect of clouds and water vapor in the Arctic by extending in the far infrared narrow bands. The classic measurements are in the window or in the 6.3 micron band. And this is there's a long story of it. It's good, but it's not enough. And in the Arctic, when the Planck function shift to the longer wavelength and the dirty window here opens up, it becomes a very sensitive modulation of the emission of radiation, especially in the winter time. So we designed this instrument with very much sensitivity, like 5 millikelvin back-body calibration, which is very similar. You see it here. It's based on uncool microbolometer. It's Canadian technology. It's used on the NETCARE missions being designed by a factory in Canada, in Quebec. And this was installed at Iqaluit at the supersite and with Zen Mariani. That's the version 2 of that FIR against order the instrument to monitor. It's still in function. And that is a site for us to get data for future missions. The first experiment was done with FIR1 and was installed at Eureka site, side by side with the MMCR, the E-AERI, and the LiDAR. And then we could validate the instrument. You can see here the instrument installation. And here's just a short example of that during one day, but they're all similar, where you can see the E-AERI in dashed line, and the solid line is the FIR, and they really match very closely. It's important to know the amplitude of the signal. It's about 9, the order of 10 watt per meter square per steradian spectral values. So any little perturbation here is detectable at almost 1% accuracy in here. So we could compare cloud and clear. You can see clear, it's flat, and cloudy, and also the spectral variation here. This instrument was flown with the Alfred Wegener Institute Polar 6 and during a campaign, the NETCARE campaign in April 2015. This was really, you can see the team here checking the state of the atmosphere. It was the first time we validate the instrument from perspective of space. So the campaign lasted 1 month across the Arctic from Spitsbergen all the way to Alert, Eureka, and to Barrow, Alaska. So then we could do profiling of, for the first time, spectral profiling of brightness temperature in different channel in the far infrared. So that was the first time we could see that. And we did compare with calculation, and they fit relatively well. The plateau you see here is when the aircraft hover at a certain level to do measurements and go up and do another measurement set. So you can see the variability in the atmosphere, but this is accurate measurements. So the idea is to do a closure experiment where we measure the microphysics or the state of the atmosphere, and we can do the calculation and measure also the result directly from the instrument. And in there we compare the measurements from the theory and make sure that it match. So that's a closure experiment that we will carry in space, because TICFIRE will be an instrument to do closure with 9 other instruments, LiDAR, radar, and other instruments in a similar way. Now, this has been combined with 2 other Canadian instruments, Ali and SHOW. Ali is looking at the limb for aerosols in the upper troposphere and up to 5 kilometer, down to 5 kilometer altitude. But in the Arctic winter, it can go closer to the surface because it's quite transparent. And SHOW is looking at the water vapor, both in a limb view, while TICFIRE is the FIR Radiometer spaceborne version, looking nadir on board the P1 Polar 1 main platform with other instruments, Doppler radar, microwave radiometer, high spectral resolution radar, LiDAR, and polarimeter. And here is the ALI and SHOW instruments that will follow on the same orbit 15 times a day over the Arctic, and especially over Eureka, where it passes very close to the station, about 4 or 5 times per day. And we also have NASA inclined measurements for time change in convection for lower latitude. So we've done an end-to-end simulator of the instrument to help on the design with the industry. And this involved doing a very close technical representation down to the pixel of the sensor and the optics and the electronics of the instruments. So we start with a high fidelity scene that is done at high resolution that we take as a ground truth. It might be a composite from observation and model. The idea is to get a scene that is realistic, that we assume as a ground truth for the moment, and try to pass our instrument, fly virtually our instruments, either from the aircraft, from the ground, or from space, any perspective. So we do detect the signal, produce a signal. You can see the different steps here, starting from input scene at very high spectral resolution, and then going to the level 0 to the filters, and then to level 1B, where we have corrected for biases and noise. And then we do go to retrieval, and there we test new algorithm for retrieval. And then we do the science impact study or the comparison. We go back to the original data and compare the result quality. And the second experiment is to add the synergy with the other instruments, the LiDAR, radar, shortwave spectrometer, and so on. And this helps us to plan and develop a space mission that really target the needs of the community. And we really need you from that perspective to tell us what is useful for science in your area. So we're very much listening about that, both in the Canadian team and I guess the American colleagues are looking for that. So to give you a little bit more on this approach is here the spectrum of the infrared. We don't look at the CO2 and ozone. It's not our objectives. We will fill that gap by using other data from other satellites or by calculation. And it's not a major constraint because it's well known to a good degree. But we're focusing with 8 bands onto the near infrared, mid infrared in the window. The standard B2, B3, B4 are standard filters, and B5, 6, 7, and 8 are new. They go as high as 100 microns. And remember that the sensitivity of radiation is close, is maximum when we're looking at targets that are close to the wavelength, like ice crystals that are 50 microns or 20 microns or 100 microns, very sensitive to those wavelengths. Furthermore, there's a lot of micro windows, and there's also a continuum that allows to do profiling in the vertical to scan at different height, at different depth into the atmosphere. And as you can see here, because of the continuum, you get a blurred image, and that's normal. It's because of that's really what we would expect to see from those wavelengths because of the continuum effect and and when you go to we go to shorter wavelength, then we see crispy and much more accurate. The instrument is meant to work at kilometer scale at very high frequency, and for SWAT of 50 to 100 kilometers around the LiDAR and the radar and all the other instruments. So one of the things we look at, I think this one is very interesting because it shows how important it is to look at the upper troposphere, lower stratosphere in the Arctic and the polar vortex. This figure represents 2 satellites. One is OMPS, which is ozone and aerosol, and Calypso, which is the LiDAR on board the A train. But when we combine the two, you see in blue the Calypso data, and in yellow you see the OMS data. And clearly you see the interaction between aerosol and cloud, both in producing aerosol in the lower stratosphere and creating ice crystal that will sediment and seed lower clouds. Even the mixed phase are influenced by the upper cloud as the crystals fall into those areas. And one of the important points to note is how important is the Arctic in terms of formation and exchange of cloud and aerosol in the upper troposphere, lower stratosphere. So those three instruments are meant to go together, looking in 3D at the perspective of the structure, vertical structure composition. And the advantage of ALI, it has a polarization, which helps us to look at the crystal shape and size and show, help to correct on the water vapor. So they are very closely interacting. Now looking at TICFIRE, for instance, the thin ice cloud FIR Radiometer that has been developed during this YOPP period, we can see here we've tested through the simulator the error range that we expect from a scene like that. We try many scenes, we have many input, but just as an illustration. And we find that it's about a quarter of watt per square meter per stereo region, which is well within the range that is needed for the mission. It's many times better. So the uncertainty is relatively small. And here you see in the long wave the radiative effect of clouds, different clouds, thick clouds, thin clouds with big crystal, thin cloud with small crystals, ice over ice, like ice crystal over ice crystal, and ice crystal cloud over liquid cloud, like in mixed phase. And that's the amplitude of one sample, just to illustrate. And the uncertainty is about the thickness of this line here. So there's a lot of variation. We're talking about the watt per meter square per stereo, an amplitude that goes nearly to 45 watt per square meter per stereo. So it is huge. And on the right-hand side, you see the spectral signature. So in the far infrared, it's B5 to B8. You see that it's still important in terms of variability. And that determines what will be the perturbation for ice, for surface energy balance, for generation of potential energy in the atmosphere, for storm generation. And this is as a signature that we can track back and trace to the composition of the microphysics in great detail. This mission is unprecedented. It will go to a detail and technology at a level that never been achieved before with this endeavor that the NASA and the international community is taking. So as an output, as a result, here you can see, for instance, the cloud optical depth from the input assume truth, which is just a purpose of work here. It could be a real one, eventually will be. And we have the retrieve one. You can see the optical depth is well captured. And one of the power of this instrument is to be able to give us ice crystal effective radius, especially in the small size at nucleation. We can look at the nucleation of ice on aerosol and pollution effect. And the microwave radiometer takes over in the range where it's difficult for us to go, because when we go larger than the wavelength, like above 100 micron, becomes scattered. And then the microwave radiometer with longer wavelengths take over. You can see also ALI, which is aerosol. Now, ice crystal, thin ice cloud is an aerosol of ice, ice being one substance in the atmosphere. And ALI sees the overlap of ice crystal cloud in the thin range, and that helps us to calibrate and do the synergy between the instruments. Another important aspect is the water profile, which also controls the water radiation balance at the surface. In the Arctic, it's fairly transparent compared to the tropics. And you can see here the effect of those far infrared band 5 to 8 that allows to do profiling. These are the Jacobian that are wave function. So these radiance can feed directly into the forecast model to improve with genuine new data the state of the atmosphere, especially in cold condition and dry condition, where it's very difficult to measure water vapor, where there's almost none left. But if we remove this almost none left, it becomes a fully transparent and the atmosphere cools very fast. So it's very, very sensitive and nonlinear. And then you can see again here the overlap of flow water vapor and TICFIRE water vapor in that range here. So this is an exercise we've done to check how useful it might be in data assimilation to add far infrared when we use AIRS as a reference, because it's one of the a good source of information. These AIRS and all the other use the 6.3 micron, which is a very narrow area, and it's very sensitive to temperature. As temperature drops, there's almost no signal. On the other hand, in the far infrared, you get plenty of signals in the far infrared. So the combination of the two goes well. It permits to go a lot longer into the far infrared, into the long wavelength and colder temperature as the time function shift to the colder temperature and decrease. Now you can see the increase. Well, the TICFIRE and AIRS add some information content, especially around the tropopause and to some extent near the surface, where it also captures very well. Now, having said that, where we started from, I mentioned that it's a large area over the Arctic. Cooling, even a fraction of a watt per square meter will translate into huge transport to compensate or to re-equilibrate the energy budget. So we're looking at the energy budget in the Arctic on a regional scale, even along orbit of the satellite. And if we take account of all the exchange term, then the Lorentz approach to this diagram using the mean flow and the eddy flow for available potential energy and eddy potential energy conversion to kinetic energy, mean kinetic energy like the jet stream, and the eddy kinetic energy like the storms. Then if we take account of all the exchange between the columns and the side, we can do a budget of enthalpy instead of just temperature, total internal energy. Now, just to illustrate here, just show you one component, the effect of radiation on some of the transfer term. We've tested the model. Model is the GCM, is the CRCM, Canadian Regional Climate Model 6, based on GEM4 from Environment Canada at 3 kilometer resolution. We used the International Polar Year because of the good data set we had during that period, and compare the simulation in terms of microphysics, cloud microphysics, and heating rate, like the input and the output. There's a lot of data, but what you can see is that the radiation is, as we expect, the leading term in the winter to produce potential energy, and it's compensated largely by transport. So, as an illustration, I just took a couple of terms where you see the effect of clouds on, like here we did a total cloud or no cloud, or actual value versus no cloud. You see the cloud radiative forcing, cloud radiative effect, and you can see here that it removed, it enhanced the cooling in the upper troposphere and middle troposphere, and does the reverse in the lower, because of the mixed phase cloud does help to warm the surface, and that translates into lateral transport that is like cloud forcing effect on transport. This is one heat term on the lateral boundary condition. It's mostly in the lower 3 kilometers, and you can see that the cloud has a very significant effect. So as a summary, the YOPP study period was very productive and successful toward the far infrared radiometer development for polar observations. And more than 60% of the radiation escaped in the far infrared, and no instrument are measuring at the moment. So now we do have a ground-based instrument that could be used in the Arctic efficiently. It's robust and autonomous, called far infrared radiometer. We have a TICFIRE in development that is progressing toward a flight in 2028 and 2030. So this is an extension, a natural extension of YOPP. And their new instrument, well adapted to cold and dry polar air, and for the first time will be able to closely monitor aerosol, cloud, convection, precipitation, and radiation together. So this will allow to improve the observation of cloud microphysics, water vapor profile, temperature, thermodynamic state at a high frequency and a high resolution, and usable for forecast model as well as for climate model to improve, especially one of the main objectives to improve the parameterization with very stringent constraint this time. So the need for the mission as overall, the TICFIRE is to produce radiative closure. That is to check that all the instruments are on the right similar track, that they give data that are consistent with anything we know about the radiation calculation, and do also quite a bit of data enhancement in cloud microphysics and water concentration. The core instrument for the HAWK is the high altitude, and I would say high latitude, water and cloud tandem. Ali show TICFIRE does 3D aerosol, cloud and water vapor interaction down to the microphysics and the nucleation of ice on phenomena like volcano or Arctic haze or pollution of different sources, and their effect on the ice surface and the weather. So the added value of the new assimilation information is also usable in weather forecasting, and it's a critical constraint for improving our climate models, as I said. And I would really like to acknowledge a special thanks for our YOPP program and its leadership. It has been a major support and essential incentive for the development of TICFIRE on HAWK and AOS mission. Thank you.
Okay, thank you, Jean-Pierre. We have time for some questions, so I'd open it up to the floor, and please go to the microphones so that we can hear those questions if anybody has some. Don't see any out there at the moment. I'll take a question then, Jean-Pierre. The observations you show are really fantastic, and I think they'll help us to improve observing and representing clouds, especially in the kind of upper troposphere region, which is hard to observe. And I think that the information on, for example, heating rates up there will be really a fantastic advancement. But I wanted to take another direction. Can you say something about the sedimentation of ice from that area with these kinds of observations? Because that's a really important parameter for a kind of climate sensitivity.
Yes, you're right. I wanted to touch about that and time constraint. It's very important. What we report as diamond dusting or clear sky precipitation is half of the precipitation in the Arctic that we don't measure. We measure as a trace. This is awful. A trace during the whole season is a large amount of the total precipitation. And this kind of instrument can help on that, because once we have the crystal size accurately enough, then we can calculate the sedimentation rate, we can calculate the mass flux of water and the dehydration of the atmosphere, I think quite accurately. So that's one of the objectives that we're carrying on, that the dehydration greenhouse feedback and the effect on precipitation. And the AOS mission is on precipitation. And it's very hard to get the Arctic precipitation when it gets down to this omnipresent diamond dusting from November to April, I guess.